Okay, let's begin. Uh, our paper is called Autonomous Wi-Fi Fingerprinting for Indoor Localization. Wi-Fi fingerprint-based localization is a mainstream solution for indoor localization. This system relies on the fingerprint map to position mobile devices. A challenge of such system is the overhead of constructing the fingerprint map. Because the Wi-Fi signal changes over time, so the fingerprint map need to be updated frequently. So this intensive overhead remains the bottleneck of the fingerprint-based system. In some designs, robots are used to perform such survey to collect fingerprints, so that the fingerprint map could be updated autonomously. They use robots in a travel with soldier way. The building is discretized into reference locations. Then robots visit and stop at each reference location to collect sufficient samples to fingerprint the reference location reliably. This because we consider the signal noise, so we need the sufficient samples. But however, this motion pattern is not energy efficient. The frequent stop of the robot prolongs the survey time and brings frequent deceleration and acceleration. Both points cause energy consumption. Using this power deficiency motion pattern, the robot surveyor may not cover large buildings because robots cannot carry large batteries and cannot be charged during operation. Our autonomous Wi-Fi fingerprinting system surveys the environment without soldier. Of course, this motion pattern is energy efficient, but it connects one sample at each location, so it is vulnerable to unreliable samples. We address these unreliable samples by our signal recovery methods. In conclusion, we can achieve energy efficiency without degrading the localization performance. Also, our system deployment is fully automatic. Next, I will describe our approach. Our system deployment includes 3 steps. The first step is to recognize the floor using the automatic snap process. Then we segment the floor map into regular shapes so that we can plan the robot survey route in these regular shapes. After deployment, the robot can perform autonomous site survey when needed. As mentioned before, collected samples include some unreliable signals. One of such signals is called lossless signal. Lossless signals are usually caused by long propagation distance and poor signal stress, but random signal loss occurs even when access points are just nearby. To recover, we recover the lossless signals using the dual band signal model. So what's the dual band signal? An access point can emit 2.4 GHz and 5 GHz signals. These are the dual band signals from the same access point. From the wireless signal propagation model, we deduce that the difference of the dual band signal is a function of propagation distance combined with Gaussian noise. So this is the following equation. The P is the signal strength, and the D is propagation distance, and the beta is the system noise, system parameters, and X is the Gaussian noise. So the signal difference is the function plus the signal noise. And we examine this equation in our environments. The bottom figure shows that the signal difference from an access point is a function of the propagation distance. Then based on the dual band signal difference model, we propose the lost signal recovery process. We first learn a support vector regression model which predicts dual band signal difference at each location. We train the support vector regression model with the connected signals. Then we use the connected 2.4 GHz signal to recover lost 5 GHz signal, and vice versa. So if both dual band signals are missed, we set them a low value. The recovery process is depicted in the following diagram. So another unreliable signal is the abnormal signal. Abnormal signals are inaccurate connected signals. So before recovering, we need to find these abnormal signals. So it's called abnormal detection. We estimate the signal distribution at each location using the Gaussian process. So we actually make the Gaussian assumption of the signal distribution. Then we use hypothesis testing to find abnormal signals which disobey the Gaussian assumption. So after identification of these signals, we need to recover them. We observe that the short-time change of wireless signal can be viewed as shifting. So this, for example, in the bottom right feature, we can see that the wireless signal shifts after 3 days. So we shift signals from the last site survey to recover the current abnormal signals. Because so this is the recovery process of the abnormal signal. Then I will describe our experiments. We use the Pioneer 3 DX robot as the robot surveyor, and we test our systems in 2 environments. One is the 3rd floor of our department building, and another is the 6th floor. For comparison, we implement the survey with soldier method as the baseline, and our method is survey without soldier, and we use the signal recovery. And for evaluation, we measure the time and energy cost for the site survey, and we also measure the localization accuracy. To do this, we use 2 common localization algorithms, the K-Lear-Rister-Leber and the Bayesian method. So this is the experiment results. The table shows the time and energy cost of our method and the baseline. We can see that our method only spends nearly 40% time and energy compared to the baseline. And the bottom figure shows the localization accuracy of the 2 methods. We can see that our system achieves nearly the same localization accuracy compared to the baseline. So in conclusion, we achieve energy efficiency without degrading the localization performance. So then we check the individual effects of the 2 signal recovery. We first check the effects of loss signal recovery. We can see the top figure. We can see in the top figure, we can see the loss signal recovery effect on the fingerprint map. The red points are the major signals, and the black points are the loss signals. And the orange line is the fingerprint map constructed with sufficient samples, so it's reliable. And the blue line is the fingerprint map constructed with the connected signals and the loss signals. We can see that the blue line, the fingerprint map constructed without the loss signal recovery, it's weird. The loss signals change the shape of the fingerprint map. And in the top right figure, we use the loss signal recovery. The blue points are the signals recovered from the loss signals. So we can see that the purple line, the fingerprint map constructed with the loss signal recovery, come close to the fingerprint map constructed with sufficient samples. And the bottom figure shows the localization accuracy, shows the localization accuracy with or without the loss signal recovery. Clearly, in each case, the third floor or sixth floor, the carriers in each localization algorithm, the loss signal recovery improves the performance of the localization accuracy compared to the so the loss signal recovery improves the localization accuracy. And then we check the effect of the abnormal signal recovery. Similarly, in the top figure, we can see the effects of abnormal signal recovery on the fingerprint map. The red points are the connected signals. The black points are the abnormal signals, are the detected abnormal signals, and the blue points are the signals recovered from the abnormal signals. So clearly, we can see the calibration effect of the abnormal signal recovery on the fingerprint map. The bottom figure shows the localization accuracy. Obviously, we can see that in all the cases, the abnormal signal recovery improves the localization accuracy. So our presentation is over. Thanks.